Hello, this is the fourth video in the Graph and Networks 2 series for OCR Discrete Further Maths. It covers a shortest path algorithm. For a given network, we may be asked to find the shortest path or route from a start source node to a finish or sink node, for example here A to F, that has the least total weight. So by shortest path, we mean finding the path of minimum weight. We may have a network of locations in which we want to know the shortest distance or time or cost to go from one location to another. The same algorithm will solve either of these problems depending on what the weights on the arcs represent. So the weights on the arcs might be distances, times, depreciation costs, or even petrol charges. The shortest path algorithm in this OCR Discrete Further Maths syllabus is Dijkstra's algorithm. As you can read, it was conceived and published in the 1950s. Here are the steps of Dijkstra's algorithm written in English. It might look a little complicated, so we're probably better off working through an example together. But basically, we start with permanent labels and order labels, and we need to use temporary labels. We'll explain this all as we go through. However, if you would like to pause and read the steps through for yourself, please do so now. Note that we will assign a box system to each node. On this slide, you can see that the top left-hand box is the order in which the vertices are labelled. The top right, the permanent label, which gives the distance from the start vertex, and the bottom space is used for the temporary labels as we work our way through. So on this example here, we will start with giving A the order 1, and we haven't gone anywhere yet, so it's distance 0. A connects to B and C. And we can see that the distance to B is 3, so we put that as a temporary label, and the distance to C is 5, so that again goes in as a temporary label. We only give temporary labels to those nodes which connect directly to the start vertex at this stage. We then compare those two working labels. We can see that 3 is smaller than 5, and therefore we give B number 2 and a permanent label of 3. We then look at working labels. So for example, B connects to D, so 3 plus 3 would give a working label of 6 for D. B also connects to C, and we can recalculate the distance from A to C via B. So it would be 3 plus 1 would actually give a 4, and because that's less than the 5, we would cross out the 5 and reassign a new working value of 4 to C. So now we compare the values of 4 for C and 6 for D. 4 is smaller, and therefore the order of node C is number 3, and the permanent value is 4. So basically what we're saying there is that the smallest distance between A and C is to go via B, and that total distance is 4. Having done that, we would now think about what additional working labels we could do. Well, D connects to C and is of length 1 away, so 4 to get to C and then 1 to get to D would mean that we can adjust that working label down to 5. For E, we'll have got to C and 4, and then another 3 would give us a working label of 7. We then compare the 7 and the 5. So 5 is smaller, so D gets an order node 4 and a permanent label of 5. Let's now think about the working labels for E and F. Well, you can get from A to D in 5, and then another 5 to F would be a 10. You can get from D to E in 1, so that would mean that you could get from A to E in 6, which is smaller. So we would cross out the 7 and put the 6. If a new working label was greater than one we already had, we would not replace it. We are now comparing the 6 and the 10. The 6 is smaller, so E gets order of node 5 and a permanent label of 6. 6 plus 3 would give 9, so we could actually get from A to F in only 9. There's only one choice now, so that gets order node 6 and permanent label 9. So here is a slide showing that solution. In order to get from A to F for the shortest path of distance 9 or weight 9, then we have to trace our way back through. When you are tracing the route back, you must make sure that you look at the permanent labels, the distances or the weights on the arc, and then the permanent label of where you're going to. So 9 take away 3 doesn't give 6. To work backwards from E, you know that you need, how did you get to the 6? Well, the 6 came from the 1 plus the 5, so you know you have to go back via the D, and so on. Read the question carefully and make sure that you give the route when it's asked for, and that you do actually state the length of the shortest path. Here is another example. You may wish to pause the video and try this for yourselves. So once again, we start with A with a 1 and a 0. The 0 meaning that we haven't actually gone anywhere from A yet. Then we would look and put in our working values of 8 for B and 5 for C. The C is closer, so that gets a 2 and a 5 placed there. We would then say, well, to get to D would take 9, so 5 plus 4, and to get to B would be a 5 plus 2, which is a 7. So we decrease that working label. To get to F, we would have a distance of 5 plus 10, giving us 15. Of those 3, B is the closest, so that gets order 3 and permanent 7. From there, E would have a working label of 8, and we've already come from C, so that's the only one we can add at the moment. So we are comparing E, F and D, of which E is the closest, so that gets node order 4, permanent label 8. From there we can see that E to H would be a working label of 15, and E to F would be 8 plus 3, be a working label of 11. As it's smaller, we would adjust the working label. We are now comparing it 9, 11 and 15. G is the next closest, so that becomes order 5, distance 9. G then has a working label of 10, and we then compare the 10, 11 and 15. That's the next closest, and from that we would have 10 plus 9 would give us 19 for the H, but because it's bigger we do not change the working label. So we are now comparing the 11 and the 15. The 11 is closest, so that gets order 7 and label, permanent label 11. 11 plus 12 would give us 23, which is a lot bigger than 15, so we don't adjust the H. And finally, we have H at 15. We can see that to get to that H, working backwards, we went via E, and then via B, and then via C from A. So A to C, oops, sorry about that, up to B, along to E and down to H to give us our shortest path of 15. However, you should also note that the shortest distance to F is given by 11, the shortest distance from A to G is given by 10, the shortest distance A to D is 9. So one of the nice side effects of this algorithm is that you find the shortest distance of any node from the start vertex as well. And here's the solution shown more neatly. Don't forget to state the weight of 15. So let's just talk through how the algorithm works. So the weights on the arcs can represent different things that might lead to alternate routes, possibly time rather than distance. So what are the temporary and permanent labels? Well, they're the values for the quickest or lowest route to that particular node. And if we find a lower one, then we choose that instead. So because the algorithm systematically searches for that quickest route, then the temporary one is, well, where have we gone via, from the start, via which nodes to get there? If we then, by adding extra working values, find a shorter route via someone else, that's when we replace those working or temporary labels with a new lower temporary label. Remember, we do not replace them if they're higher. So once we've got the node of the lowest temporary label we can find, then we'll make that permanent because we know that we've looked at all the possible routes up to that point. So once we know that there's no shorter way of getting to the node you're currently at, then you can assign the neighbouring nodes a temporary label. The first node gets a permanent label 0 because you haven't travelled anywhere yet. And at the end of the algorithm, each node has a permanent label representing the shortest distance to that node, as we looked at in the examples. If two nodes are joined, then the difference in their permanent labels will tell you the shortest distance between them. So you can also interrogate the network once you've got all the labels there to answer other questions of distances between other nodes. I have a few points about Dijkstra's algorithm. It's not always necessary to label every node. Dijkstra's can be used on directed networks, but do look out for the directions of the arrows when assigning the working labels. So this algorithm finds the shortest path from your starting node to all the nodes that get permanent labels on the way. Therefore, it's not terribly efficient for the purpose of sat-navs because it would take far too long, and you've probably seen the speed at which your sat-nav works. So sat-navs would use more complicated and heuristic algorithms. Dijkstra's algorithm, if you go on to do A-level and come across dynamic programming, is not as adaptable as dynamic programming, which makes the best decision at each stage. So although Dijkstra's algorithm is a good way of finding a shortest path, and it is the only one that this AS syllabus covers, be aware that there are other algorithms which are better. Common errors applying this method are not adding new arcs onto the permanent label value, writing incorrect temporary labels or replacing them with larger ones by mistake, not working from the last label that was made permanent, not realizing that when working back you can freely choose if two vertices are equally likely, i.e. they both give the correct arithmetical answer in terms of working out the route. Some networks have directed edges. You can still use Dijkstra's algorithm for these, provided you respect the directions specified. Occasionally networks contain negative lengths, i.e. if profit outweighs cost on a particular route. Now, Dijkstra's algorithm does not work if a network contains any edges of negative values, so watch out for that. This was the last video in the Graphs and Network 2 series.